I'm happy to introduce Dr. Simon Emmanuel from the Institute of the Earth Sciences. Simon is senior lecturer at the Institute of the Earth Sciences at the Hebrew University. He completed his master's study at the Hebrew University and his PhD at Weizmann Institute of Sciences. And his postdoc at Yale University at USA. Simon was awarded by numerous awards and fellowships, like Golda Meir Fellowships at the Hebrew University of Jerusalem, Bateman postdoctoral fellowships at the Yale University, and the Dov Elad Memorial Prize at the Weizmann Institute of Sciences. And main research interests are water-rock interaction, archaeogeology, and petroleum geology. Please.
Okay. Thanks, Gina. So today I'm going to talk about, as you can see, extreme limestone weathering rates of the Western Wall. If you were to take out the word extreme, it would probably be more accurate, but the reason I put extreme in because it sounds more interesting. So first of all, let's start a little bit with why carbonate weathering is even important. Now, we know from our experience in this part of the world, this could be anywhere in the Mediterranean. In fact, I have no idea where it is, but it could be anywhere in the Mediterranean. And you can see here typical features of what's called karst geology, karst topography. Karst topography is basically, for those of you who aren't familiar, is the formation of caverns, sinkholes, caves, all kinds of things that are generally ascribed to dissolution, okay, by water of carbonate rocks. Okay, so we're familiar with the caves and various things, but basically, generally, if you open up any textbook on geomorphology or karst geomorphology, you'll see this reaction a lot. That's calcium carbonate reacts with CO2 in the atmosphere and water, and basically you get a dissolution reaction. So you get calcium ions formed and bicarbonate ions formed. And I think this is pretty much as far as we're going to go into geochemistry today. But basically, this is generally thought to be, this dissolution reaction is thought to be the main way that we get the formation of these caves. Okay, so dissolution is a main feature. And obviously, if we increase the amount of carbon dioxide or we increase the amount of water, the idea is that we can get more and more and more dissolution. So of course, these are, it's this reaction which is thought to form these amazing, fantastic caves and cave systems all over the world in carbonate rocks, and it's quite a spectacular feature. But it's not just of interest in a kind of academic way, or if we're geomorphologists. The water-rock interaction actually has major practical applications, and some of the major practical applications involve, today especially, when we're talking about injecting carbon dioxide into the subsurface in order to remove it from the atmosphere. This carbon sequestration, what you're basically doing is you're taking carbon dioxide, you're dissolving it in water, you're creating very corrosive water, very acidic water, and that can then react with the rocks. And there's a lot of interest now going on into basically how this reactive water, how it behaves when it's in contact with various different kinds of rocks. Also, another practical aspect of it is in petroleum geology. Okay, so they actually take one of the main methods used today to extract even more oil from the subsurface is by injecting carbon dioxide. It's actually a very cool way for the oil companies to get some double accounting out of it, because what they do is they basically get carbon credits for injecting CO2 in the subsurface, and they're able to extract no petroleum. Okay? So they love this method, and it's also very effective. During this reaction as well, there's water-rock interaction. It dissolves that part of the rock, it can change its permeability, it can reduce it in some areas, enhance it in others. So there's a lot of interest in what goes on with carbon dioxide-rich solutions in contact with carbonate rocks, for example. Okay, so on a global scale, it's not just something that we see in this part of the world. 15 to 20% of the continental surface is covered in carbonate rocks. This is a map of the carbonate rocks, and you can see them all marked in red. everywhere on the surface of the planet we're going to find, we've got a reasonable likelihood of finding carbonate rocks. So it's a global phenomenon that we're looking at. But it also has one other thing that people are very interested in is its impact on climate. Okay, and this is actually in the last 5 or 6 years has become something that has really been come to the forefront in trying to understand carbonate reaction with carbon dioxide. So when we're looking at the geological carbon cycle, generally people think of carbon dioxide reacting with silicate rocks. And that acts as a pump of sucking out CO2 from the atmosphere. And over geological times, this reaction is actually been thought of as controlling climate. Okay, so when we have more weathering, we take out more carbon dioxide and we actually reduce carbon dioxide in the atmosphere. And the idea is that this is one of the things that has been changing over time and regulating the amount of carbon dioxide in the atmosphere. Okay, so a lot of people are trying to, for example, connect this reaction to snowball Earth, okay, and various other periods of time in the geological past. One of the things that's been completely, basically pushed aside is this reaction. Calcium carbonate reacting with CO2, it's the same thing, okay, producing bicarbonate. Now, one of the reasons people have said this is because, okay, it's only 15 to 20% of the surface of the Earth. But if we look at this map, actually what we're seeing is we're actually seeing a map of geochemical hotspots. And what do I mean when I talk about geochemical hotspots? I mean that this is actually a map of the most reactive rocks on the surface of the Earth. And carbonates react much faster than any other rock. Not by a factor of 10, not by a factor of 100, but by a factor of about 1,000. Okay, so if we're looking at short periods of time, 10 to 100 to thousands of years, maybe this is where we should be focusing our attention. And in fact, some estimates put the amount of carbon dioxide being sucked out of the atmosphere by carbonate rocks as exactly the same number, and even more than is being sucked out by silicate rocks. Okay, so there's a lot of interest now going on actually in how carbonate rocks interact with carbon dioxide in the atmosphere over periods of 10, hundreds, thousands of years. Okay, which up until now has been pushed aside because silicate weathering has been the main focus. So these are some of the motivations behind why we're interested in carbonate weathering, and especially the rates of carbonate weathering. And if we're going to talk about the rates, we're going to go back to this equation here. Again, calcium carbonate reacting with CO2 and water. And there's been a lot of effort put in over the last 30 years into trying to figure out what the chemical reaction rate is. So we've got a chemical reaction rate, and this was going back to the 1978 when Plummer came up with it, and he said, okay, it's connected to the concentration of protons or the pH, and there's some linear coefficient, the concentration of bicarbonate ions, and the concentration of calcium and carbonate ions. And he said basically all we need to do is do enough experiments, we can figure out what the K1 is, we can figure out what K2 is, K3, K4. Once we know that, we know everything about the carbonate system. We know exactly how fast it's going to react. All we need to do is do some experiments that can determine K1, K2, K3, K4. And there have been dozens and dozens of papers that have tried to do this. And some of them with quite a lot of success. But the question is this really, if we know everything about this equation, if I know K1, K2, K3, K4, if I know the chemical reaction rates, does that actually tell me anything about rock weathering? Okay, and that's, up until now, up until I'd say the last 10 years, people said, yeah, that's all we need to know. One of the problems is that all the experiments that people did basically involved these two things, powder or perfect crystals. Okay, and they did experiments on powders and they did experiments on perfect crystals, and they figured out the kinetics based on these two things. What very few people did was actually look at rocks. Okay, they didn't take rocks, they took powders and crystals. And if we look at rocks, actually rocks are quite different. Okay? They're made up of crystals that are stuck together, they're individual grains, and maybe they react differently. In fact, if we look closely, this is an atomic force microscope image, which I'm going to show you more of later, But basically what you can see here is a topographic image. These are grain boundaries, these are pores. Look at the scale here. So this is 1 micron. We've got these tiny nanometer scale pores. This is actually limestone, close-up of micritic limestone from the Judean hills. Okay, so it's nothing exotic, it's just typical limestone. And we can see this crystal here, and it's tiny. And the question is, does this behave differently? Does this react differently in different rates to those perfect crystals or powders that we saw? And if you look at the data here, this is Cornelius Fisher, and he published this in 2012. It's 3 years ago. This is in Geochimica, Cosmochimica Acta. Okay, so we're not talking about some small journal here. We're talking about 3 years ago in a leading geochemical journal. Okay, and he published this image here. This is 10 microns. This is a picture of a map of a dissolving calcite crystal. And so what you can see here, these are called etch pits. Where it's blue, it means there's been more dissolution. Where it's red, there's been less dissolution. These are etch pits. Look at the scale here. Over the experiment, 20 nanometers. It's not very much. These etch pits are very unknown, and they're related to the crystal structure. He then did a really simple, he then took a bit of limestone, did the same experiment. And this is the map that he got. So we're looking again at a map of how much the surface is dissolving. And you can see here we've got these these regions here that have dissolved more than the blue, and the red where there's been little dissolution. Look at the scale, it's 3 microns. Okay, so it's dissolving much quicker. We don't have any of these patterns that we had before. It looks much more random. If we look at what's called if we look at the distribution of rates, so here we've got the rates along the x-axis, we've got the frequency of those rates along the y-axis. We can actually see 2 different curves. So this is the curve for the crystal. Okay, you can see here the average is that red dot up there. It's much smaller. It's about 0.1 on this scale. And micrite, that's the fine-grained calcium carbonate rock, falls about there, about 1. That's its average there. So we've got a factor. We've got rates that are about an order of magnitude faster in the rocks. Okay, an order of magnitude faster. It's not something small. And one of the things that Fisher said, he said, okay, we get this difference, and the reason we get the difference between these 2 shapes is still geochemical. It's a geochemical mechanism. Okay, and he said the reason is because basically, if I look at a crystal, okay, different parts of that crystal are going to dissolve up at different rates. Okay, so the edges are more reactive than the faces, and the corners are more reactive than the edges, and these different parts of the crystal basically are going to determine how quickly it dissolves up. If I have more of these edges, it's going to dissolve up much more quickly. And that was their explanation. Different parts of the crystal, basically if I have more tiny crystals, there are more of these edges, it's going to dissolve up faster. That was their explanation. It sounds very reasonable. But the question is it true? Okay, we look at this image here, you look at the scale here, we were talking about 10 microns as the scale bar. It doesn't give us enough resolution to actually see what's going on. We just get a map. We don't actually see what's going on in these pits here. We don't actually understand how these pits are evolving. It still looks like quite a random process. So that was their hypothesis. When we came along, we did some experiments to try and test what was going on. So in my lab we have an atomic force microscope, and what it is basically a microscope that scans the surface with a very fine tip, and it actually feels the surface so you can get a topographic image of what's going on. What we did is we put a tiny chunk of rock in there, and we look at the fluid going in, we have fluid going out, and we actually monitor the surface throughout the experiment. So we don't have to stop the experiment, we keep it going the whole time. This is a schematic of what's going on. We're pumping fluid and using a syringe pump. We're scanning the surface using this needle, tiny needle that has about a 10 nanometer size at the end. And we're collecting the effluent at the end. And basically, this tiny needle, we can see how it moves, and we can actually get a topographic image at the end of the day. So this enables us to actually see what's going on. So one of the things that we do in order to help give us a reference frame, because we need to get some kind of reference if we want to figure out how fast this surface is dissolving up. I coat part of the surface with gold. Okay, it creates these gold islands, and those surfaces then become inert. Okay, they don't change. They give us some kind of reference topography that doesn't change throughout the experiment. Okay, so just to show you a very short movie of what's going on, you'll see it changing from blue to red, and the areas that are blue don't change, the areas that are red are dissolving up. And you can see, this is dollar stone actually, not limestone. You can see these chunks, or basically these pits that opened up very quickly. Okay, I think we'll move on. And I just want to show you what happens with fine-grained limestone. So here we've got an image, or you can see these polish lines, okay, before the experiment, and that's what the surface looks like before. This is what it looks like after close to 100 minutes. Okay, you can see these grain boundaries that open up. Okay, and what we can do is, because we have a reference, we can actually subtract one topography from the other, and we can get a map of the reaction rates, which is what this is. So here we're looking at a map of the reaction rates in the different areas. And so we see here along the grain boundaries there's been it dissolves much more quickly. Okay, which is what Fisher said should happen. We should get much more rapid dissolution along the grain boundaries. And within the crystals we get much slower rates. So that's fine. That's what we might expect. One of the things that we saw when we did these experiments over and over and over again, we saw something that really surprised us and quite frustrated us because we didn't know what we were seeing in the beginning. But basically what I'm going to show you now is something called, well, we call it disappearing crystals. And what I want you to look at here is this crystal here. So this is the masked surface, this is the gold surface. These are crystals here that have that you can see the grain boundaries have dissolved away a bit. And I'm going to show you what happens after a few minutes. So keep your eye on that crystal. This is 4 minutes later, this image. This is another 4 minutes. So it's 8 minutes have passed. Another 4 minutes. And then another 4 minutes. Okay, so basically, in this scan, the crystal's basically half dissolved. Or it appears to have half dissolved. What's actually going on here, we're scanning using the rastering method. Okay, so each line takes a second. It sees the crystal here, sees the crystal here, sees the crystal here, and then it's gone. So within the space of a second, the crystal's gone. Okay, it's just disappeared from the surface. And then of course, I want to show you that this crystal also goes eventually. Okay, they all basically dissolve up.
What are the scale?
So the scale here is about, I think it's 15 microns, 10 microns, something like that. So basically that crystal here is about, I think it's 3 or 4 microns in size. So it's a pretty small crystal. This is micritic limestone. So what do we think is going on? So we have dissolution. We start off with a rock like that. Imagine that this is a cross section. It dissolves along the grain boundaries. Okay, and then at some point, that crystal basically detaches from the surface. Now, actually, this mechanical or physical detachment from the surface, not chemical. There's no mechanism that can explain the size of 3 or 4 microns disappearing like that. It has to be physical or mechanical mechanism. So we're actually having removal from the surface. It's not chemical. Okay. Now this is actually something similar to something proposed by Marsh and Shashel in 1960, which was related to which is related actually to electrochemical effects. When you have an electrode, okay, when you have an electrode and it's basically dissolving up, it actually you should be able to calculate how much mass is lost according to how much current you pass through the electrode. But what Marsh and Shashel knew is that this is never the case. More mass is always lost, or is often lost, than can be accounted for by the amount of electrons being flowed through the electrode. And they said it has to be some kind of mechanical disintegration of the electrode, which is basically what we're seeing here. We're seeing a mechanical disintegration of the surface. And so this is actually a simulation of the chunk effect from the electrochemical literature, which is 2011. And the idea is that basically these chunks are floating off the surface. Okay? And it looks very similar to what we see in our limestone. If we take, this is again fine grain limestone, each one of these grains is about 5 microns in size. This is what the surface looks like using scanning electron microscopy after 6 weeks. Okay, we can see that, we can imagine that there's some kind of similarity between what we see in these two processes. This is 50 microns here for those of you who can't see. And we can see that the surface basically looks as though chunks have come off it. It started out as an entirely smooth, polished surface. Just to show you that it's not typical of all calcareous rocks or rocks with calcite, this is marble. Okay, same scale. Okay, the same lateral scale. You see, it looks completely different. Okay, we have much larger crystals. It doesn't look like this. Okay, now one of the things that we saw is that attachment, only in our experiments at least, we only see it in very small micron-sized grains. Now it could occur in marble, but it's going to take much longer, if that is the mechanism, because it has to dissolve up much more of the grain boundaries. The other thing that we see in our experiments, we know with our experiments are laminar. Okay, so it's not an effect that's a result of turbulent flow. Okay, so this is laminar flow. The effect might be even more enhanced in turbulent flow, but it's certainly not related to turbulent flow. Now, Yael Levinson, a student of mine, wanted to quantify this. So far we've just got very qualitative a mechanism, but we want to actually see how much does this contribute to the overall effect. So what she did, she looked at areas where there was only dissolution. This is time, and this is the surface retreat, how much the surface on average is retreating in that area. And she looked at areas where there was only chemical dissolution, where no grains appeared to fly off the surface. And this is red line here. And then she looked at the whole field, okay, the whole field of view. And that's the black line here. And you can see, of course, the black line is much faster, is dissolving, is retreating much faster than just the areas where chemical dissolution is occurring. And what she found out that she did when she did enough experiments, she found out that on average, it's about 40%. That is, 40% of the overall rate is related to the detachment of grains from the surface. Okay, so if you were to ask a geochemist, he'll tell you, yeah, that's what happened, that's what should happen, but in reality, it's the black line. We're adding another 40%. Now, 40%, when Yael came to me and she told me that it was 40%, she was very disappointed. She wanted it to be an order of magnitude or something like that. And I said, no, 40% is great. It means that half of all your dissolution, okay, is actually a mechanical process, which is fantastic. And if you open up any textbook, you won't find any mention of this. Okay, this kind of mechanism for calcite or carbonate rocks. Okay, so this is actually, although it had been, people had suggested it and said it might occur, this is the first time that it actually quantified, and we can put a number to it. Okay, so, and that number that Yael came up with was 40%. So far that's all very nice. We've seen this in the lab. But the thing is, does it occur in nature? And of course that's what everyone wants to know, does it occur in nature? So ideally, in order to test this idea, we need an experiment that does two things. Firstly, we want an experiment that lasts for thousands of years, okay? Because reaction rates are very slow. You saw we're using an atomic force microscope, we're measuring changes in nanometers. There's no field technique to measure such small changes at the moment. So I want something that's going to average the process out over thousands of years. That'll give me some indication of what's going on. And I also want something that's going to have both fine and coarse-grained limestone. I want to see whether or not this mechanism also occurs in coarser-grained rocks as well. It's one thing to have fine-grained rocks, but we want to see whether it's a function of the texture of the rock as well. So these were the two things we wanted to look for. And luckily for us, we actually have an experiment like that, not too far away from us. And that's the Western Wall. Now I know it sounds a bit crazy, but there are a couple of features here that that make it a pretty ideal geochemical experiment. Okay? And one of those features is that some of the rocks, if you look up close, they really haven't changed very much in 2,000 years. And if this is one one of the Herrodian rocks, so we know pretty much it was laid about 2,000 years ago. And you can see this frame here. Now this frame is actually part of the original frame that was chiseled out 2,000 years ago. And it hasn't changed very much. You can see here and here. It hasn't changed very much. On the other hand, there are some rocks that are also from the same period, that are also Herrodian, and they've eroded away completely. Okay? They've completely eroded away. You can see here, a rock underneath it, for example, still has its chiseled border. In this area, a lot of the rocks are eroded. This still vaguely has an outline, but some of them are completely eroded away. So the question is, first of all, the first question was, can we actually say something about the rates? Okay, afterwards, we'll try and talk about the mechanisms, but we wanted to say something about the rates. So what we did is we took a LiDAR scan. LiDAR is basically a laser scan of the surface. Luckily for us, we didn't actually have to do it ourselves. Apparently, the Antiquities Authority commissioned a scan of the wall about in 2008. They did it again in 2010, so there are 2 scans of it. And they didn't do anything with the data. And I actually contacted the company that did the scan. They used the most high-resolution LiDAR that they could. And they said, well, actually, you can have the data. You don't even have to pay anyone for it because they commissioned it from us. And the Antiquities Authority never paid us. So you can have the data for free. So I got, I don't know, a scan that's worth $10,000 or $20,000 for free. So sometimes all we have to do is ask. You ask, you get. Don't ask, you don't. So basically, LiDAR is a method that's used in geomorphology quite a lot, just to look at changes over time. Usually people go to places, for example, cliffs that change very, very quickly. So, for example, or dead cats. The Geological Survey is looking at the way cliffs erode from year to year. And that's a technique that people have used. People haven't really used it to look at buildings or rocks because they erode too slowly. So if I go from year to year, for example, the scan from 2008 compared to the scan from 2010, we can't see any difference. Okay? But we can do something else. So this is what it looks like. This is the area. We don't have a whole scan for the whole area, but we have a scan for part of it. And this is what the scan actually looks like. You can see here that this is how far it is, how deep into the wall it is relative to some kind of reference. And you can see that the colours get darker and darker as you go up. That's because the wall is a bit set back, okay, to prevent it from falling over. So you can see that some of the regions are very well, highly eroded. Now we're only going to look at the bottom sections, okay, because basically all the rocks from here downwards are Herrodian. Those are 2,000 years old. Everything up is recent, relatively, okay. Also, all the rocks above here don't have this framed border. Okay, so we're only going to look at the Herrodian stuff. So how do we quantify erosion rates? We went with a reasonably simple idea, which has been around for quite a while, but no one's actually done it with a LiDAR scan. Imagine this is a cross section of the original rocks. So we're looking at these are the borders, the chiseled borders that we can see. So if we find a rock that still has on either side 2 relatively well-preserved rocks, we can actually create some kind of false datum. Okay, we can take the data, we can tilt it, and we can recreate what the surface should be like. And then any deviation from that surface will be the amount of erosion. Okay. So this is basically what we get. So we get a map. Again, you can see on either side we've got the well-preserved rocks. What you're seeing here is a map of erosion in those rocks. So yellow means there hasn't been very much erosion. Dark colours or red means there's been more erosion. And then when we look at the frequency, so we're looking at the retreat rate versus the frequency. Again, this is similar to the kinds of graphs you saw before. We see a peak here, and we can calculate its average and various things. Okay? And basically, what we get from 4 rocks that we were able to do this on the Western Wall, we get these rates. The Western Wall, these rocks in particular, erode at 24 millimeters per 1,000 years. Okay, these are just these rocks here. The Judean hills, according to a completely different technique, okay, we're looking at cosmogenic isotopes, the same area, produces 21 millimeters per 1,000 years. It's you know, it looks like we cheated the numbers, but that's what we get. Then you compare it later to something else, what's called the potential chemical weathering. So you take all the rain that falls in Jerusalem, and you tilt it and you throw it against the wall, okay? And you see how much I can actually dissolve up, assuming that the carbon dioxide is the same level. That's all you get, 13. Now, well, he says, okay, well, this is because the carbon dioxide is different. We have various different things that we have, vegetation, etc., that increase carbon dioxide. But this is for uncovered rocks, and this is uncovered rocks. There's no way that we're going to increase, we either have to increase the amount of rain, or we need some other mechanism. Okay, we can't get from here to here just by, without doing something different. Okay, we're not going to, there's no mechanism that can increase the carbon dioxide, because the wall has basically been like that forever. There's nothing that's going to do that. We know the rain has been pretty much constant over the last few thousand years. So that doesn't leave us with many options. And I think the only option it really leaves us with is mechanical disintegration. Now, of course, if you look at that, the other reason I think it's mechanical is that if you look at these rocks, why would chemical reaction prefer that to that? There's no actual reason. If you look at the lithology, though, I think that's where we'll find the answer. These are coarse grain limestones, and these are fine grain limestones. Okay, they're actually quarried from the same area, but these are much finer grain. Okay, and this is coarse grain. So anywhere you see the well-preserved chisel, the chiseled borders, basically it's a coarse grained rock. And by coarse grained, I mean about 50 microns. If we look in scanning electron microscopes, this is 9 millimeters. You can see it's very porous, these rocks. These fine-grained rocks, you don't see anything. You need to go to much higher resolutions before you start seeing something. And this is what the fine-grained rocks look like, the micrite. So we've got about 10 microns, 5 microns crystal size. So we think that kind of fits with this idea that mechanical disintegration is what's controlling what's going on here. Now, we didn't just want to stay with this idea, we also actually wanted to test it. Okay, so we couldn't go to the Kotel and start chipping off chunks of it. I tried to persuade one of my students to do it. He wouldn't agree. Afterwards, apparently, people from the Antiquity Authority said, if you'd come to us, we would have been able to find bits and pieces for you. And say, if you don't ask, you don't get. So I didn't ask and I didn't get. So we went to a place called Ramat Shlomo in Jerusalem, which is where they found quarries that they think, archaeologists think, supplied much of the stone for the building projects in Jerusalem. The thing, this is a picture of what it used to look like. You see this stone here, which was kind of abandoned. So they think those are the scale of the stones that were quarried there. That's what it looks like today. There's a school built on it, and they've left part of the rock there for austerity. You can go to some of the quarries still available. It's still there. Another part of the quarry is being destroyed by a road they built in Jerusalem. The quarry is getting smaller and smaller. But this is an image here of what the quarry wall, what it looks like today. You can see how rough it is, okay, and how much erosion it's gone through, which is a story in itself. You can see again he's looking at something here. Let's see what he's looking at. There, that's a stylolite. I'm going to come back to that a bit later, again for you, stylolites. And we're going to see how they affect the story. Okay, so we went and we sampled these rocks, and we did some experiments on them in the lab. So we did the same experiments using our atomic force microscope. We look at the way the surface is changing. So this is what it looks like. Initially, you can see the grain boundaries, okay, and 4 minutes later, there's a hole in it, okay. Basically, there's a chunk missing. We've got the same mechanism. This chunk effect also occurs in these rocks. So there's at least circumstantial data suggesting that this acceleration by mechanical disintegration also occurs in these fine-grained rocks at the western wall. But I think there's also more to it than that. And if you look at a lot of these fine-grained rocks, you can actually see these kind of crack-like features called stylolites. They're basically diagenetic features. They form in the rock when it's been compacted. And if you look up close, you can actually see these squiggly bits. It's called stylolites because they look like someone's taken a pencil and scribbled on them. At Tel Aviv University, by the way, at the new synagogue they built there, they have the 2 columns outside made of limestone, and they use stylolites in them to simulate the kind of writing on a Bible scroll. So just to see, if you look here though, there are all these kind of chunks missing from it. It looks like it's the same kind of mechanical disintegration but occurring at a much larger scales. So this would be about 1 millimeter. And if you go up to any of these rocks, you can actually start peeling them off. So mechanical disintegration might, at a larger scale, might be what's controlling what's going on at the Kotel. Okay, or maybe it's a combination of small scales and large scales. So if we just look at the rates across the scales, so this is all the data from the western wall that we had. So looking at the frequency, and looking at the normalized rate. So we're averaging the rate, we're dividing the rate by the average of the rate. Okay? So 1 is the average, 2 is 2 times, 3, 4 times, etc. So that's all the data that we compiled. And that's what it looks like when we look at the cumulative probability. So we're just summing the probabilities as we go along. And that's the curve that we get. This is what we get from laboratory experiments. Now, these aren't my laboratory experiments. These are Fisher's laboratory experiments that he did in that 2012 paper. And he also worked on micrite limestone, and he also worked on there's a completely different micrite limestone from Germany. And he gets, using his experiments, reasonably similar curves. Okay? And I suppose the most amazing thing about this is that, well, A, it's non-Gaussian, okay? And B, there's quite a similarity. Now, what does this actually mean? We're looking at scale here. The scale here is 50 microns. The scale here is 1 meter. What does that actually mean that we're seeing a connection between such 2 different scales? Does it mean that these two processes are comparable? I'm not sure I have the answer, but it would seem to indicate that mechanical processes might be occurring both at this scale, which we can see, and this scale, which we infer from what we see at the outcrop. Okay, we can see chunks missing at the stylolites, etc., etc. We know, for example, these are stylolites. Everywhere you see the kind of horizontal red line there, that's a stylolite. So maybe this mechanical process is occurring at various different scales. And that's, I suppose, the idea that really I think is interesting. We don't necessarily have a 100% handle on what's going on, but it seems that a lot of these areas that we see of high levels of disintegration, I call it disintegration, not dissolution, weathering, they're probably controlled by mechanical processes. Okay, or what we call chemomechanical. Why chemomechanical? Because we need the dissolution to start to be able to remove the chunks. So going back to this question, do we see it in nature? Well, we saw it at the wall. Can we see it in nature? Are these caverns that we see here, is that a chemical process like the textbooks would tell us? Or is it a chemomechanical process? And we still don't have a good answer to that. But my guess is that it probably is. Okay, my guess is that the mechanical processes are occurring here, and then they can't be completely ignored forever. So if we're going back to this map here, okay, and this map of the global scale, if mechanical processes, and if they're really as large as we think, if they're at least 50%, and the Western wall would actually tell us that they're more than that, they're a factor of 10. But I'm saying if we're going to the conservative value from our experiments, that tells us it's about 50%. Maybe everywhere on this map that we're looking at, when we're trying to measure dissolution rates or trying to measure weathering rates, 50% of what we're measuring is actually a mechanical process that was completely ignored up until now. And I think that's the issue. It's not so much that, when you tell people, they go, okay, it doesn't sound, sounds reasonable that mechanical processes occur. But no one has quantified it, and you won't find it. I was amazed when I looked at this 500-page book called Karst Geomorphology, 200 pages devoted to geochemistry. They don't mention mechanical processes once in the whole book. And this is considered the Bible of Karst Geomorphology. Right? So, everyone says, yeah, it sounds reasonable, but it's not there. And why is this such a big deal? If we're trying to figure out rates of processes and we're trying to figure out how much climate change is affected by all this, a factor of 2 can be an important thing, okay? Or even more. Now, away from the science, when we first worked on this and when we published it in geology, we got very excited about it. We worked quite a lot on a press release because most of my stuff is not that exciting that you're going to get any kind of interest from anyone else who's not a geologist in it, and even geologists, you have trouble getting them interested. So we worked quite a lot on this, and I got a phone call from someone from Arlet, and he says to me, "So can you tell me a bit about your work?" I said, "Well, basically, we're looking at the way rocks are eroding and all this kind of stuff," and I realised I was losing him. So I kind of said, well, basically, it's about 2 kinds of rocks. One's the good rock, and one's the bad quality rock. And I kind of joked and I said, I think it probably means that Herrod got screwed by his contractors. And then so what do I see then 2 days later is the running title of the article is Herrod ripped off by Western Wall builders. So anyway, that's what happens when you talk to, you try to do your best work, and this is what. By the way, I don't think, I mentioned this to some archaeologists, and they said there's no way Herrod was ripped off by his builders because he had overseers. He had people who were making sure that he didn't, no one would dare rip him off. So just like today, right? I mean, no one rips off any builders. Anyway, builders don't rip off anyone anyway. So the other thing is the way you can tell the poor quality rock here is the stylolites. Now that's something you do actually see in outcrop. It's something you do see. The builders would have known. Okay, but that was still not the main story. Anyway, so coming to the conclusion. Basically, what we see from our experiments is that micron-sized particles detach from surfaces. That's something that we see, and that enhances the weathering of these rocks. Not only does it enhance, one of the interesting things is it could even be the dominant mode of weathering on a global scale for carbonate rocks, which would be a very interesting thing, and certainly contrary to what most geomorphologists think about it. There are actually quite a few implications for estimating not just chemical weathering rates, but also for heritage conservation. If we want to preserve the way, if we want to preserve buildings or archaeological sites, then we better understand what the mechanisms are, controlling the way they erode. Another interesting thing is the contaminant transport. Okay, so these rocks are actually they're releasing colloids. Now those carbonate colloids, they actually are very reactive and they can absorb heavy metals and various other things. Now if we thought that those things were stuck to the side to the rock fracture wall, now actually they might be mobile. They might be transporting things in the system, which is again an interesting thing that we was beginning to look at. And of course, oil and gas recovery. Okay, so we're looking at how the release of colloids can then affect permeability, porosity, and various things. So there are quite a few implications for this process for various other things. And of course, I think the last conclusion is, of course, this: be careful when you talk to Chinese. So. I think with that, I'd like to thank Levinson, who's a PhD student of mine. She's been really very prominent in doing all this work. Without her, it would have been impossible. Evgeny, who helped me with a lot of the field work, and Eitan Sass, who taught me the difference between the rocks in the Jerusalem area. And of course, the Israel Science Foundation for funding me. So, thank you.
Thank you very much, Simon. Any questions, please?
Well, I have one question and maybe one remark, sort of. The one question is, when you compare Judean rocks versus the wall, the difference is exactly the direction of the rain, as well as the amount of vegetation, which would probably increase the amount of acid. So the question is, can you quantify that, or is it possible, because you're talking about two different ways of weather?
The orientation, yeah, so that's a really important point. The orientation of a rock is very important to the way it weathers. I mean, we know this from when all you need to do is go to the quarries, by the way, and you can see they've got a corner, and you can see the top is weathered in a completely different way to the sides. Okay, so we know. So everything that we're seeing here, I mean, when I said the rate is similar, the rates compared with rocks that are uncovered, with no vegetation, no soil cover, in the Judean hills. The orientation, though, is probably they're reasonably horizontal. So the orientation is not comparable. So one of the things is the western, also the lithology is not exactly comparable. For example, we didn't go, these are average for all carbonate rocks that were measured in the Judean hills, not specific to the Netzer formation or anything like that. We're actually, Yael is now looking much closely at that, how these cosmogenic isotope rates compared to what, so she's taken the same samples that we measured, and she's actually dissolving them in the lab and seeing if there's any relationship at all to the rates that you get in the cosmogenic. My guess is there won't be. Which is in itself an interesting thing, but we'll find out in the next few months.
Maybe another. If you take a much older site, for example, comparable, do you think the rates would change in a certain way, or would it be linear?
I don't know. I don't know. I mean, 2,000 years is a long time, so it seems that.
But if you take a 6,000 years old site.
Again, I don't know. I really have no idea. I mean, my guess for carbonates, no. I think for other rocks, probably yes, because they go through, because the minerals themselves change. But I have no idea.
Another orientation question. Do you see any differences, especially on the western wall, if the rocks, like if the stylolites are vertical or horizontal? No,
well, this thing, I mean, the western wall, you actually do have horizontal and vertical. Okay, so you can see, they've cut the rocks sometimes like that and that. Where it doesn't, wherever you have stylolites, you have increased erosion.
You don't see that if they're vertical, that they're more.
I can show you the images, and then that's the. Where are we? No, well, that's a funny thing. So here you can see horizontal ones, for example. Here, okay, so you can see sometimes they're vertical, sometimes they're horizontal. There seems to be no relationship.
About this photo, there is an historical fact that until 1967, all this region was
up until here.
Only until there?
Yeah, so that was covered up until here. After in 1967, they excavated basically further down.
But furthermore, there was a neighborhood over there.
Yeah, there was a neighborhood about basically here. Up until like an alley about 2 meters, 3 meters wide, close by. But the amount that was excavated, you can see from historical paintings that it was up until there. You can see the rocks in the historical paintings, and you can see but it was excavated by about 2 meters. But that means that this was street level then. So yeah, there was this. I wouldn't have taken a scan of the Western Wall. I would have gone either to actually this part of the Western Wall, for example, this is actually taken past Wilson's Arch to the corner, basically the southwest corner, and also along I would have scanned also on the southern wall as well, because there is a fear that somehow people were there and exacerbating. This though was never worshipped at or treated at or was never. This is basically probably as close to what you're going to get to the natural erosion of the wall. The problem is they don't have a scan of this data.
There is also the effect of the wind direction from the south wall and the west wall.
I think it would be very interesting.
And also, I think there's also, it more looks like the Muslim quarter now. It was more higher in some places, so the wind maybe was not as. So maybe it what shows you that on the lower part you see much less erosion than the upper part. Maybe the wind there was more.
There doesn't seem to be, the main correlation between the erosion is the lithology. I think it would be interesting to go to actually map or to do a scan of all three walls, because of course there's the eastern wall as well. And the problem is it's getting money to do that kind of thing. We also don't, it sounds simple, but you point something at the Temple Mount and it looks a bit, and people say, what is it? And you say it's a laser, and they go, ooh, right? There's that, but I actually think it's a very, one of the interesting things is that most places, most archaeological heritage sites in Europe, for example, have already been scanned years and years ago. And now, here, we still don't have a scan of the most important heritage site in Israel. But
I was just about to propose.
Sorry, just after that.
Yeah, did you try to track those missing chunks in the outflows? That would say that it's totally mechanical. I mean, if you track them.
Okay, so it's what we need to do is it's not as simple as it sounds, because you basically need a particle analyzer at your outflow, which we don't have. Also, I'm not sure what level of sensitivity you need. It's one of the things we plan to do is to hook up a particle analyzer to it. But yeah, that's. And
another question: you said that you expect finer grains to erode. That's the slide. Finer grain limestone to erode quicker. But you say that the stellarites erode quicker. I would guess that the stellarites are a coarser grain, from what I remember. That's
actually start in the net cell. Okay, so basically this is net cell, and this is oh God, what is it? It's not sorry. No, well, Bina is what they used to call them. Yeah. It's Netzer and something else now, right? So basically, the stylolites are actually where you are only in Netzer. They're not in shifter. That's it. They're not in shifter. They're only in Netzer. So you don't. And why you find out is because fine grains, it's micritic mud. Stylolites usually form where you have at least a layer of, you have some amount of clays. So if you're talking, this is basically a high energy grain rock, grain stone. This is low energy kind of micritic mud so you don't. So that's why you actually don't have any stylolites here, because there's no clay. But that Regina could probably tell you more about how much you need, how much clay you need in order to get.
Calcite grains are coarser in the stylolite. Of course you got the clays, but
they're not. They're not actually. Okay, that's the thing. Also, there's one of the things we wanted to have a look at is we wanted to see if in the literature there was anyone who actually looked at grain size adjacent to stylolites, because we thought maybe you've got a higher concentration of small grains, and it's something we haven't done. No one's looked at. I don't know, but certainly fine grains with stylolites is generally accepted. It's not a strange phenomenon.
Last question. Who else returns?
How this work changes or reflects on the idea that CO2 increase in the atmosphere on global timescales is connected to erosion of mountain belts. For example, because you are saying about 40% less.
No, okay. So in terms of the geological timescales, a lot of over geological timescales, people have said, well, probably carbonate weathering doesn't make a difference anyway, because you have precipitation of calcite in the oceans, or aragonite in the oceans, and that gets buried, and over geological timescales it all evens out, because what gets buried is equal to what gets eroded, so we don't have to worry about that. But over shorter timescales, you can have an imbalance. And I think that's what people are interested in. So over kinds of millions of years, it probably doesn't make a difference. But one of the things that people have suddenly said is, hang on a minute, if I want to understand how weathering changes over periods of 10 or hundreds or thousands, maybe this is what's going to save us from global warming. I'm not saying it will. But then there's been a lot more effort trying to quantify the rates.
Yeah.
Okay, so the one rates that are one of the things people do is look at rivers and they look at concentrations of calcium and bicarbonate, etc. But the other thing that people do is try to look at denudation rates and then use that. So everything that's basically eroded must be in a chemical form. And then you have to be really careful then.
But it's not, what you're saying is that it's not, that 40%.
Yeah, so I'm saying basically it would mean that it's less important as a CO2 extract.
Yeah.
So that's.
Okay, thank you very much, Simon.